Thank you so much, and thanks for the invitation to talk here. I'm really excited about our project, bringing computation to the climate challenge, and I'm here on behalf of the whole team, my co-lead Raffaella Ferrari, and a suite of faculty across MIT from different schools and also the College of Computing, not all of whom have worked on climate before. So this is really a team that tries to get at climate as an information challenge, climate as a knowledge challenge, and really understanding what we need as a society to provide information on climate for the future, not necessarily for the past. So again, this is part of the grand challenges, which you heard about from Professor Lester, so I'm not going to repeat that, but it's again one of five flagship projects that are part of that program. And what's important about the grand challenges, and like climate in general, is that it's really a whole of MIT initiative. And this is because in the past 10 years, we've really realized that climate is a cross-industry, cross-awareness. It affects everything. It affects everyone's lives. And so when we think about climate modeling, you can think about weather modeling as sort of a precursor, and a lot of the early weather models were developed here at MIT. So here on the left, there's the Earth seen by NASA satellite. On the right, if you can press play on the video there, we have the Earth simulated by NASA model. Oops. There we go. We're starting to get there. What you'll see is you can see that there's a dynamic simulation of clouds and water moving around. And that's a combination of really advanced modeling that has been developed over the years and a lot of computational infrastructure, but good playback between data and model as well. And this kind of fidelity that uses really advanced computational modeling is really critical to how climate models have developed, but it's also useful for people. And this is the idea that we're trying to harness in the Bringing Computation to the Climate Challenge proposal. So why do I say you need climate information? Well, think about why you might need weather information, and then go to a longer time scale, and this is where you might need climate information. So this slide comes from the Intergovernmental Panel on Climate Change and illustrates the sectors that are connected to climate. 10, 15 years ago, I might have come and said, okay, so the industries that are relevant to climate, okay, energy, maybe agriculture, those are really directly connected to weather. I think we're increasingly realizing, and you're probably realizing this in your personal life as well, as you see the frequency of disasters and extreme weather events and climate impacts accelerating, and they're accelerating more in the future, that climate is really connected to a broad variety, pretty much everything we do. So this is an example, water filtration, health, tourism, recreation, issues of clean air, any kind of natural resource that you're thinking about that's part of your business or your well-being on Earth is really connected to the climate. And as part of that, the Intergovernmental Panel on Climate Change has mapped out how climate change interacts with society. The decisions that we make today determine the future climate in the longer term. Climate has impacts on ecosystems, but there's two-way feedbacks across this whole system. And if you're really going to understand what the climate is going to do, it matters where you are. It matters what those feedbacks are and how to map that out. To understand those feedbacks in the future, we need models, we need analyses, and we really do need a next generation of models. What we have right now are models that were essentially designed to tell us about the problem and tell us in broad scales about the problem. A lot of the models that we've been relying on to make climate-related decisions are one size fits all models. There's a suite of global scale climate simulations, and they're typically used, and you probably are familiar if you've seen a bunch of different projections of climate out into the future, that there's a few scenarios. You look at different trajectories. This is, for example, global average temperature. And they will project temperature at different places in the Earth. But it takes a long time to run these models. And I'm guessing that none of your companies has necessarily the capability to run a climate model in-house. Very few people do. And it's not that common to think about, OK, let's go run a climate model if we have a climate-related question. Right? And this is really a problem because you'll need climate-related information to make decisions on all of the different sectors that climate addresses. And that information often isn't as accessible as we'd hoped or tailored. And there's a really big barrier to running a climate model. When we have students come in, we have to teach them the ancient computer languages that a lot of these climate models are written in. It doesn't leverage the latest computational languages or infrastructure. And it's a big, heavy lift in terms of the computational power. So every different question you want to ask, could take months to get an answer. The urgency of the climate problem means that we really don't have months and years to wait for these kinds of answers. We need to be making decisions now. So that's really the challenge we set out in our grand challenge, is to think about, well, we have an example of this, right? We have an example from what MIT has done in the past in those weather models, which are increasingly leveraging data and much more highly resolved and also very useful. I guess none of you have run a weather model either, or maybe a small number, but probably all have a phone in your pocket, and chances are you might use a weather app pretty regularly. You're stuck in a room like this all day. You're thinking, is it raining outside? Do I need to put on my raincoat? You can get a projection. You can also see whether it has a probability of raining during your commute home or during the day, or what the real field temperature is outside, for all different locations. But you don't need to have to run the whole weather model to get there, right? So the vision of this project is to bring the machinery and the sort of understanding of climate modeling really to be more relevant, to be more useful, and to address the climate challenges of the modern era rather than the climate challenges of the last several decades. So the first step in this is to develop a better climate model in the first place, and this is where colleagues of mine have worked on the CLIMA model, the Climate Modeling Alliance. This is an MIT joint project with Caltech and NASA JPL. And this addresses some of those challenges from a climate modeling standpoint, really developing from the ground up a better climate model. And part of the challenge and part of the innovation of this climate model is that it can ingest data. It can have a better representation of the uncertainties of the climate system, better probabilistic projections, but also runs on latest computational facilities and can also take advantage of the latest in AI and machine learning to help those projections. So this CLIMA project started a couple of years ago, and when we launched the Climate Grand Challenges, we said, that's great. It's great to have a better climate model, and that solves part of your problem, but it doesn't solve all of your problem. Part of the problem is that these kinds of models aren't that accessible and usable, and aren't providing the climate information that increasingly everybody needs. Again, separate from weather information, which is on the shorter term, what about longer term? Do we have reliable probabilistic predictions? Can you get the outputs you need? But also, can you get the outputs you need in a way that's flexible? So you can say, OK, what decisions that you make are affecting those outputs? And we didn't have the facility to do that in any kind of accessible way. And when I say accessible, I mean low cost, timely, and tailored. So tailored to the specific outputs or regions or decisions that are interesting to the user. But also do that flexibly, so we're not designing one thing for one user that isn't necessarily useful for the other, because then that doesn't that doesn't meet our criteria of flexible and low cost because, we took 2 years to develop something that was very, very tailored, but then we'll need another 2 years for the next user, another 2 years. And there's basically, if everyone needs climate information, we really want to democratize that. We want to make it more useful and more available. And what we know about designing models, and any of you who design models in your industry context know that models are useful to the extent that they're developed in context and with users in mind, right? You need to understand what goes in, what goes out, what can be usable. So the idea is that we'll take this CLIMA model, which we're referring to here on the left, and use advanced artificial intelligence techniques to develop emulators of those models. So basically, fast-running versions of that big climate model that are targeted towards projecting the variables that are of key interest to users and stakeholders. So that might, in one case, be rainfall in a particular region. It might be wildfire risk. It might be drought. It might be heat impacts. It might be a combination of heat and air quality. But the key innovation here is to develop those surrogate models quickly and, to the extent we can, automatically, so that the query of the parent model, the fully formed climate model, can be kind of done in the background. And specific information that's relevant to you, similar to what you have in terms of your options and how you've already set your weather app, can be accessible that quickly for climate information. So that's really the goal, and that's how we're thinking about moving on with this project. I want to give a concrete example of some of the work that I've done in thinking about climate and air quality to just give an example of how emulators can be useful and the kinds of questions that link climate to a different sector that can help inform decision making. And so my example on how emulators can help, given that this is a sustainability conference, thinking about connections between climate and some of the sustainable development goals. So if one of your goals is to prevent health damages from air pollution and at the same time ensure access to energy, climate change is linked to both of those because it addresses availability of energy in the future, and the externalities of energy lead to air pollution and health damages. So you can think about that being connections between 3 of the separate sustainable development goals. How do we understand how climate change leads to one or the other? Well, we need models to understand that. We need models to understand how the decisions on climate change percolate into changing temperature, changing wind speed, changing the conditions of the atmosphere, but also at the same time, the decisions that are made to reduce greenhouse gases intersect with that. So it's a really complex system. And in order to understand that, we need a whole suite of models, and those models take a long time to run. And we know, because we've done these really complex long-term models, and other colleagues of mine have done that, that climate policies can have great benefit to human health. And a major way they do so is by reducing air pollution and related mortalities. So there have been a bunch of studies that rely on combinations of climate models with other kinds of models, including air quality models and projections of mortalities associated with air pollution that link decisions that you make on the climate, 2030 up to 2070, with impacts, reduced mortalities, other kinds of studies that have been done. And if you look at sort of the number of studies, though, like 3 to 5 studies in this big review paper. Part of the challenge of doing some of these studies is that the modeling infrastructure that you need to do this, it takes a lot of computational time. It takes a lot of effort to link those climate simulations to the application that you care about. And this is an application that lots of people care about, right? But it's hard to understand climate in the context of that when the climate information is difficult to access. So this is a study that I did in my group that sort of is the baseline, sort of giving you a sense of how complex it is to do some of these analyses. This is a study that I did sort of in partnership with the US EPA. And they were interested in how mitigating climate change could affect future air pollution and related mortality increases in the US. So this was back when the US was deciding on goals, for example, for the Paris Agreement, and thinking about the degree to which mitigating warming in the future could mean that we have fewer hot days. Fewer hot days mean fewer opportunities for air pollution to undergo some complex chemical reactions in the atmosphere and increase, those hot and stagnant days where you get a high air pollution alert. The number of those likely to go up in the future if there's climate change. So what kind of benefit could climate policy have for that? And in order to figure that out, we needed to run a suite of climate models. And when you run a suite of climate models, you need to run enough so you get a sense of the statistical properties of uncertainty. And we did some uncertainty analysis on this. And we actually did 150 different climatic years to figure this out. Previous studies hadn't done really enough climatic years and didn't have a robust enough estimate of what happens in the out years to really be useful from a policy perspective. Because if you think about it, you make a decision, you reduce emissions, and then it happens to be a hot summer. Were your emissions reductions actually effective or not? You really need a statistical simulation to really figure that out, right? And we did that, and it was run by then postdoc Fernando Garcia Menendez. He's now a faculty member at North Carolina State. It took him about 2 years to get those simulations running. And this was a question that was really timely and useful for EPA. But it wasn't a question we could address in a very quick way with the modeling infrastructure we had. So lots of people have very similar questions like this. And not a lot of people have 2 years, a postdoc, and a very large supercomputer that MIT can use at their disposal. So what we want to do is we want to make this kind of analysis. What happens? What happens to my sector if climate change is mitigated? What happens with a decision that I'm making on a climate variable I'm caring about? And then how does that affect downstream some of the models that I use in my industry? We want to make that easier on the user. And so that's really the goal of the project. And so we've been starting out some of this work in the air quality and climate field and really thinking about new models and methods to do that. So one of the strategies is again, this ensemble approach, a reduced form model, where you can think about it as kind of creating a surface, right? And you can think about different levers. One of those is the climate lever, other decision levers that are useful in the problem, and then see how that affects an outcome. And you can really think about that, plotting as climbing the surface or going down a surface, and then thinking about what decisions you need to make. Now, it's a lot simpler to just plot out where you are on a surface and make that really accessible to people, even if it's an n-dimensional surface, than that complex kind of climate model where you have all of the different fields resolved on a 100-year timescale and have to run it every time you have a different kind of question. So this approach of thinking about emulators can help us get to a place where we can develop a new state-of-the-art model, but also bridge that with usable tools. And eventually, we can connect climate in that way with multiple indicators and outcomes relevant to sustainability. So we know that climate feeds into all sorts of things that you're caring about, whether it be food production or energy or life below water, for example. There are all sorts of existing simulations and existing modeling approaches to address different sustainable development goals and different ways in which you can use your impact to promote well-being. But connecting climate information to that has been historically complicated. We want to make that easier. We want to make climate information as accessible, again, as the weather app. So as we think about this idea, we're really hoping that this is embedded in MIT's idea of thinking about climate as a whole of institute problem. So again, the accessibility of a climate model. Of course, we're going to need advances in science to make those climate models more robust and more high fidelity. But increasingly, climate models aren't just going to be the domain of climate scientists. Climate models are going to be tools of the future, and we need to have those tools be the most advanced possible in terms of computational infrastructure, taking advantage of the latest in AI and other kinds of advances, and be able to bring that to climate science, but also bring those climate models to use. So in that context, in the grand challenges, we're hoping to partner with companies who have test cases that we can use to actually say, okay, so what kind of climate information is usable for you? And ideally, a range of those. So we've been talking to companies that have used climate information and saying, what from that big climate model might you be interested in? What have you used in the past? Have you worked with consultants who have put together sort of climate projections for you? How difficult was that process? Were they tailored enough for your needs? What would you really ideally like to have? What kinds of levers would you like to explore in terms of their impact on the climate problem and its implications for your own business? And then hopefully with that emulator approach, we can design an interface between the big scale climate model, the new generation climate model, the Klima project, and user needs, so that we can provide that climate information in a flexible way, provide that infrastructure that's going to meet the challenges of climate information out into the future. So with that, I just want to thank the team, which comes from a bunch of different MIT departments, and leave time for questions. Thanks.
Well, thank you for that. You could see all the different collaborators on those logos of different departments and centers at MIT. So this is really a cross-departmental emphasis, just like you said the climate grand challenges are. So we have some audience questions. The first one that's gotten a couple of votes about challenges translating between the different stakeholders. I think that's the one. Oh, I got one vote. I think there was one that got two, if you could go back a step here. That's it. Yeah, how might this approach improve the goals of embracing change?
Right, that's a great question. We're working with lots of groups across MIT that connect with stakeholders on the ground. And one of the groups we're working with is the group that has developed the En-ROADS model. And that might be familiar to some of you. It's a simulation that has been used with audiences worldwide to understand how changes in the energy system affect climate. And our approach is really kind of a back end to think about how we can provide more detailed information similar to their kinds of approaches that will bring in a very sort of streamlined way information that might be regionally or industry specific when you're engaging with one of those sort of climate models. So, it's one thing to say, okay, if the government does this, then the global average temperature is going to go up. But when you look at, for example, a sea level rise projection of a place you care about, or the number of hot days expected in a place where you have outdoor work going on, that really brings climate to practical decision, but it also will, of course, motivate action, because you'll realize that this has a very clear and sort of monetizable impact in some ways, and a very personal impact.
Okay. One that was very unique here was about, the second one from the left. How would these models help commercial and industrial sectors address the requirement for climate-related financial disclosures? So is this tailored to a point that they could use this in a way they're not now?
We'd be really interested in doing a pilot project around that, and we hope that it will be helpful information. I mean, I think right now, in terms of climate-related financial disclosures, the kinds of climate information that might be accessible to you might not be tailored in a very specific way, and it might not be feasible to get in the time frame of the disclosures and changing of those disclosures. So again, those climate outputs are going to differ industry to industry, which ones are relevant. And not all of those might be available from the database of climate modeling that was designed several years ago to try to be the one-size-fits-all for everyone. So we really have the opportunity to provide sort of tailored products, one of which could assist in figuring out what the climate-related risks are financially.
And you said you are looking for industry test cases and partners to.
Absolutely,
so,
yes.
Okay, there you go.
Yeah, I hadn't thought about that particular test case, but that's a great one.
So the other one, what are the challenges translating between stakeholders in industry and the other stakeholders, academic, government?
Yeah, that's a big challenge that we think the MIT approach really sort of is driven from. That, you know, climate modeling really shouldn't be just the domain of academia and government, right? It shouldn't be just, you know, fifth-year graduate students and postdocs that are able to get climate information, and really democratizing access, because lots of people, sure, developing those models will continue to be an advanced academic pursuit, but the use of those models really applies broadly. So I think some of the challenges are really awareness and getting a broad range of stakeholders to really understand the urgency of the climate problem, but also to get academics to think about what kinds of advances in a climate model are really going to help advance decision-making capacities. What kinds of resolutions are really needed? And that actually varies industry to industry. It might be okay to have a fairly wide probability range for some industries, and a lot of uncertainty around that. For others, it might be the opposite. The better probability, the better value you can achieve, and better decisions you'll be able to make. So again, that's part of those challenges, but the model quality is really critical for that, and that's why we leverage the CLIMA project.
Okay. I think this is a good place to stop here. So thank you, Professor Selin.